Today, we will learn how to design a PID controller using Pole Zero Cancellation to control a second-order system. This is your control theory teaching assistant. If the system is a second-order system, we can use a PID controller to control it. First, multiplying P by C PID yields an open-loop system with 2 zeros and 3 poles. And our goal is to select appropriate values for Kp, Ki and Kd to cancel 2 poles with 2 zeros and leaving only 1 pole. Here, we can derive that Kp over Kd equals A and Ki over Kd equals B. Using the formula, we can determine that the closed-loop system is a first-order system. If the desired closed-loop system is a first-order system with omega bandwidth, we can establish the equation C times Kd equals omega bandwidth, and solve for Kd equals omega bandwidth over C. By combining this with the two previous equations, we can solve for Kp equals A over C times omega bandwidth and Ki equals B over C times omega bandwidth. If system is a second-order system, you can use a PID controller to control it, where Kp, Ki and Kd can be obtained using the following three equations. The closed-loop system will become a first-order system with omega bandwidth. But is that all there is to it? Not quite. Did you remember in the last video, we mentioned that a controller with more zeros than poles cannot be implemented? The derivative term in the PID controller is an example of this. Therefore, a low-pass filter is usually added to the derivative term. Additionally, a derivative with a low-pass filter is a high-pass filter. To implement a high-pass filter in MATLAB's ODE solver, you can separate the pole and zero into two transfer functions, one representing the state of the filter, and the other representing its output. By using these two equations, you can implement a high-pass filter in ODE 45.